It turns out that what you're going to find is you would have to quadruple. There's a square term here, or a square root term. Your time will go down by half if you quadruple the mass. So, okay. So what you guys saw, you guys kind of saw that. So you have this funny relationship. So it's not as simple as doubling the mass gives you half the time. It's a little bit more complicated. But let me just talk a little bit, just one more thing about motion. If you're accelerating, one way of thinking about the velocity is that the velocity equals the acceleration times time. Does that make sense? You start from 0, at time equals 0, your velocity is 0, and you increase velocity with time linearly. Does that make sense? Maybe? So this is what happens in a constant acceleration situation. Is that all this equation means is that your velocity is increasing the same amount every second. Okay. All right. Quadrupling the weight. If folks have other questions about some of this stuff. All right, do people do the rubber band?
Yeah.
So the rubber band.
That wouldn't be true if you're falling, right? That wouldn't be true if you're falling to gravity.
So what would be true?
Velocity equals acceleration times time. Is that and be linear? Okay.
Yes.
Go ahead.
No. It's a good question. Well, the
Well,
reason that it doesn't sound right is because you're thinking of, so position versus time is definitely not linear. It's, right? But the velocity as a function of time is increasing. The speed as you go down is increasing by the same. When you drop something, okay, so when you drop something from a height, all right, in metric units it's 10 meters. It's roughly 10 meters per second squared. So you're increasing velocity by 10 meters per second every second. So the first second you're going 10, the second you're going 20 meters per second, the third second you're going 30 meters per second. So that's the linear relationship. Does that make sense?
By the way, just to add to that,
Yep.
at the high school level, we don't use meters per second squared. They have to tell me meters per second per second.
Right.
Because that's how much it changes
Yeah.
by every second.
Yeah.
And for example, if you threw something in the air and you gave it an original speed of 30 meters per second, they can tell me that it's going to go at the end of the first second, it'll be at 20 meters per second because it's decreasing as you're throwing it up. At the second, they can even tell me at the third second it's stopped and coming back down again, essentially. Acceleration doesn't change, but instead of using meters per second squared, we'll use meters per second because in their minds, in kids' minds, it makes more sense to see that it's a change per unit of time.
Do you have them literally graph that out?
They graph it.
So you really take it bit by second by second by second?
We do that, and in fact, we do it also with the camera where we'll measure it, and we're able to do some things along that line. But that part's in the high school part. For this part, for where you are, it's much more important to know that at a constant acceleration, that change in speed or velocity, however you want to say it, is the same every second of its flight or its movement, whatever it may be. That change is very consistent.
And that's
it's
what's
hard calculus if you want to change any of that.
Right. Right. So I absolutely. I think thinking about acceleration is meters per second, or feet per second is a more intuitive way of thinking about it. And I also, the other thing to point out is this is another thing that's special about what Newton's laws are telling us, that if you have a force on an object, something very specific happens. Its velocity changes every second by the same amount. Okay? And that's what acceleration means. That's what constant acceleration means. Okay, so the self-propelled car is really something kind of different that's happening there. So let's talk about the self-propelled car. So, what makes the car go? What makes the car go? Yours the car didn't even go. It went backwards. Well, it went somewhere. So what makes it go?
The energy in the rubber band.
Okay, the energy in the rubber band is absolutely a great answer. So there's a whole bunch of different ways we can answer. So what do you? So that's great. So what? The energy in the rubber band. Where's the energy in the rubber band come from? You said that.
Winding the
Tension. Don't. So we're going to do a whole thing on energy in another day. But I want to keep talking about this a little bit. So when you stretch a rubber band, talk to me about energy in the stretching of a rubber band. What's the energy? Stored energy. It's potential energy.
Less.
Yeah, it's a particular kind of potential energy, which is elastic. So what do you mean by potential energy? What does that mean?
It means
Stored.
yeah.
You said it. I didn't mean to jump over because you said it already. That's the only reason you said stored, which I think is great. So what that means that it's
building up. I mean, the more you wind it, the more it's storing, and then when you let go, it becomes kinetic and it releases.
great. So it becomes kinetic. What's kinetic mean?
Moving.
Okay. Okay, that's great. So the rubber band is sort of the energy storage unit of this system. But since we're dealing with forces in motion, let's talk. Oh wow, we only have a few minutes left.
Yeah, we need about 5 minutes to wrap.
Okay, let me just do real quick. Let's talk about the car. All right. When this car is moving, when we release it, how would we describe its motion?
Accelerating.
It's accelerating. Okay, so if it's accelerating, okay, let's do the balance of forces. I'm gonna go ahead and do this one because I think you guys. All right. What are the forces? What are the forces on the car in the rubber band case when it's accelerating? Is there a net force on the car? Is there a net force from outside the car on the car?
None.
Does everybody agree with that?
Yeah. Outside the car.
There's the table.
If there was no outside force on the car, what would be? If there was no net force, if there was no net force on the car from the outside, what would we know is true?
It would be stuck.
Okay, hold on. Let's be careful. I've heard that it would be still and it would not be moving. I don't think that's what you mean.
Because the wheels could be spinning.
I think you mean that it would not be accelerating.
Oh.
Okay. Constant velocity also. So when you have no net force, it can also be going at a constant velocity. So if there is no net force on the object, then it can't be accelerating. So you just told me it's accelerating. So where's the force from the outside coming from?
Friction.
So why don't you say that louder? What?
Table and tires. Depending on, I don't know which way your car's going right now.
Okay, my car's going this way. That's a good point. I won't draw that because that looks like a force. The car is moving in this direction. So what? You're telling me that it's the table and tires. So external to the car, what's applying a force to the car?
The table, external.
The table's actually pushing.
The table's
The
pushing.
table is pushing the car?
Yeah.
Yes.
Okay, right. What direction?
In the direction of
The-
the motion.
That you're going.
That way, the opposite direction of the tire.
In the direction of the
Which is the
acceleration.
way
Tires
you're
pushing
going.
backwards. That way.
Yes.
I like that. The tire's pushing backwards and the table's pushing forward. This is where you have to be careful about which object you're talking about. So from the table's perspective, there's a force pushing that way, right? If you're the table, you feel a force pushing that way. You got to do that. You got to think about it that way. And if you're the car,
Do the
the table's pushing you that way. It's just like when you're walking. When you're walking, you push off the floor, right? The floor is pushing you, you're pushing the floor. All
And
right.
if it's something slippery underneath of you, the force moves that object, right? Like if you have a piece of paper and you put, the object will move in the opposite direction you're going.
Exactly. You'll slip right up, and you'll. So yeah, exactly. So again, you want to think about this is like it's like the case, and some of you got to it and some of you didn't. We'll maybe do some of that next time, where you push against something and push against a wall. There are equal and opposite forces being applied there. Okay. And that's exactly what's happening in a tire. That tire is not spinning. There's no relative at the point of contact. The tire is actually stationary relative to the floor, right? That's kind of strange to think about it that way. But the tire does not slide. It's stationary relative to the floor, and it's pushing off the floor, and the floor is pushing it.